Welcome everyone to physics. We are going to talk about how to solve some 2D motion problems. We're going to go through this worksheet called 2D motion in class problems. It's linked via Canvas right above this video, in this video as a PDF. So if you're on the video virtually, you're going to want to access it that way. When we go through and we set up these problems, we're going to want to treat these problems a lot like we did with 1D motion. We want to read through the problems. We want to underline and look for key information. We want to look through the problem types, and based upon problem types, we can then come up with additional variables. Then we choose our equation and we solve. Okay, and that's how we set these problems up. So today I'm going to kind of model how to do a couple of these. They're really, remember, a 2D motion problem is nothing more than a 2D motion problem is two 1D motion problems that are happening simultaneously. So things are moving in the x direction and the y direction at the exact same time. There's two types of 2D motion problems. There's a projectile motion problem and a non-projectile motion 2D problem. So if we're just, when we were talking about that ball, the bowling ball rolling across the floor and curving, that's a 2D motion problem, but it wasn't a projectile. Projectile motion, we'll go with the racquetball today. Projectile motion is like this, right? It's moving freely through the air in two dimensions, where 2D motion would just be, like if this is my x and this is my y, you know, the ball moving like this is 2D motion. Or I could go like this is 2D motion. Okay, so there is a difference. So when you're going through problem types, it can be 2D without being a projectile. So the first problem, almost all of the 2D motion problems we do are projectiles. Let me just make sure that's up. So 2D motion in class problems, I would encourage pictures. They seem to help, in my opinion. I'll try to color code some stuff because I think that's kind of beneficial too, at least for the modeling aspect of it. So we have a tennis ball, number one, according to your worksheet, says a tennis ball rolls off of a 0.8 meter high table at 1.2 meters per second. How far from the edge of the table does it land? So we have a table, we have a ball, the ball is rolling towards the edge of the table. The table is 0.8 meters tall, and the question is, how far from here to here is it? Now, if there was no gravity, this ball would go straight up forever. It would never stop. That's what happens in space. Once we get that thing, like that rocket ship, that space probe going in a direction, it just keeps going straight. We don't have to keep rockets on. We don't have to keep pushing it. It's going to move at a constant velocity unless an outside force. And like, it gets too close to another planet, then it'll deflect. Okay, but that's the idea. If there was no gravity, it'd go straight. But there is gravity, so the path of this thing goes something. Oops, I should probably have it land. It does something like that. Now, this says a ball rolls off the table at 1.2 meters per second. Now let's, for a second, go and say, what if a car drives off of a cliff? The car's driving at 55 miles per hour when it drives off of a cliff. It's the same idea. The ball rolls off the table at 1.2 meters per second. You can say, well, why would a car drive off a cliff at 50 miles per hour? It's for a movie. There's no one in it, and it's for a special effect. We'll go with that. Or it's a stunt person, and they have their helmet on and seatbelt. They'll be perfectly fine. Don't worry, no one gets hurt in any of these physics problems, ever. So, but that's the idea. If a car were to drive off a cliff at 55 miles per hour, it's driving this way at 55 miles per hour. It's telling you how fast it was going right here before it went off the cliff. Same thing here, the ball rolls off at 1.2 meters per second. It's rolling on the table at 1.2 meters per second. So I'm going to use my red marker for like stuff from the problem. So that's stuff I was able to pull from the problem. We haven't identified where they're going to go for my variables yet, but we will. So now we look at our 2D motion problem types. Really the first thing we have to decide, is it a 1D or is it a 2D motion problem? And I really hope you pick 2D motion. Most of our problems are going to be 2. There are a few, sometimes they'll throw in there like, hey, just don't forget, we can do 1D motion problems. This is how we do a 1D motion problem. Oh, this is a max height problem. We're going to use one max height problems when we do this. So there's a few times, but the unit's 2D motion. So keep that in mind. Most of these are going to be a 2D motion. So is it a 1D motion problem, yes or no? No. Good. No, you're right. Whoever said that, thank you very much. No, it's not. Okay, so is it a 1D motion? No. Wait, I don't even remember what question I asked. Did I ask if it was 1D or 2D? I hope I said 1D. Did I say 1D? Okay, I said that right. Good. Whew. Okay. Is it a 2D motion problem? The answer is sure is, Mr. Davis. Good. You know, the funny thing is, and I think it's funny, you guys think it's just weird, whatever. I try to not move my mouth when I do that, so you can't see me doing that, but I could be a really bad ventriloquist, and I could move my, I guess you could. Anyways, let's do that. So it's a 2D motion problem. So because it's a 2D motion problem, and I know it's a 2D motion because it's moving through both the X and the Y direction at the same time, simultaneously. So I know that, so because of that, I need to make, and I'm gonna use black for this. Because it's a 2D motion problem, I'm gonna fill in all my information that I can gather with my black marker. So I make a list of both problems. So I have a delta X, VIX, VFX, AX, and Z. And I have a delta Y, I have a VI, Y, I have a VF, Y, I have an A, Y, and I have a T. The last thing is because they're moving simultaneously through both the X and the Y, is moving down in the same time interval as moving left and right, my times are going to be the same. The amount of time it moves in the X is the same as the amount of time in the Y. Black marker is done. My green marker is for the next problem. Is it a projectile or is it not a projectile? So the key to knowing whether it's a projectile is once that ball leaves the table, is the ball moving freely through the air in both the directions? And when we say freely through the air, we're saying the only force acting on it is gravity, and there's no air resistance, very simplified you know. But the idea is the only force acting on gravity as it moves freely through the air? And the answer is yes. So because it is a projectile motion problem, then I'm going to use my green marker. We can go through and we can fill in some information. So because of that, we can say my acceleration in the X direction is 0 meters per second. And basically what that's saying is there are no forces in the X direction, therefore my velocity in the X direction is going to be constant. Because my acceleration in the X direction is 0, it says my VIX is equal to my VFX. I often make this, it's like bracket, and I write same. And you don't have to. You could write a value in for both of those, just realize that they're going to have my VIX is equal to my VFX. I often do that just because I think it visually is a little nicer. Okay, and then it also does say, and just kind of something to keep in the back of your mind, is we're probably going to use equation number 3 for the X direction stuff. Just kind of keep it back of our mind. Okay? Because it's a projectile motion problem, we also know the acceleration in the Y direction is equal to negative g. Now, if we're on Earth, then it's negative 9.8 meters per second squared. And unless I tell you otherwise, we're on Earth. However, if we did go to the moon, then our g would have a different value. If we were to go to Mars, it'd have a different value. Change planetary objects, then we have to change our value of g. That g is location specific, but we're talking planetary. Whatever. Planetary doesn't quite work because of the moon, but it's based upon like a moon versus Earth versus a different planet. Okay. So that is because it was a projectile. I can use my green marker. Now, there's 2 types of projectile motion problems. There's horizontal launch, and there's an angled launch. It's one or the other. It can't be both. It's one or the other. So we have to ask ourselves, does this ball, is it a horizontal launch? Where some examples, the object is thrown horizontal to the ground. Example would be like a ball rolls off of a table. Yeah, that's a good one. A car is thrown flat. I'm sorry, a ball, not a car, a ball is thrown flat, or a car drives off. Is it that, or is it an angled launch where the object is thrown at some angle above, so it's not horizontal? And it says a ball rolls off a table. It doesn't say a ball rolls off a ramp, it says a ball rolls off of a table. So because of that, I'm going to use a blue marker to fill in all the information because it's a horizontal launch. And because it's a horizontal launch, my initial velocity in the y direction is 0. And what that's really saying is as this ball is rolling towards the edge of the table, and as it rolls off the table, how fast, as it first leaves the table, how fast is it going up and down? And the answer is, it's not moving up and down at all. The initial velocity in the y direction is 0. So the blue number represents because it was a horizontal launch. Now I'm going to go back to my red. My red marker I drew for the information from the problem. We're going to be able to now put some of these numbers in. So there's really 3 things. There's a question mark, there's a 0.8 meters, and there's a 1.2 meters per second. We just kind of figure out like where these go. So this is a meter, that's the displacement. We either got to figure if it's a delta y or a delta x. So is it up and down, or is it left and right? Well, I'll talk about being high, so that's a delta y. Something to keep in mind, displacement is a vector quantity. And because it's a vector quantity, we need a direction associated with it. And we either need a plus sign or we need a minus sign. Now, if it's a plus, it's implied we don't have to put it. But is this ball going in the y direction? Is it going up 0.8 meters? Or is it going down 0.8 meters? So therefore, it has to be a negative 0.18. Okay, and I put it here just for contrast. I will put it up over in this list of variables in red. So the ball is going to go down negative 0.8 meters. That's our delta y. How far from the edge of the table, so from here to here, well, that seems like how far. That also seems like something we measure in meters. So that's going to be a displacement, and we've already decided this is a delta y. So hopefully you can identify that's a delta x. There's my question mark. We're solving for delta x. And the last thing is this meters per second. And hopefully you recognize that meters per second is a measure of velocity. We've already determined that it's not initial velocity in the y direction because of horizontal launch. Final velocity, or is it in the x direction? And it's how fast the marble or the tennis ball is rolling across the table. Therefore, that's my initial velocity in the x direction. But because my acceleration in the x direction is 0, it's also my final velocity in the x direction. So that's information that we can fill out. Now I'm going to tell you this right now. Most of these 2D motion problems, we're going to have to do 2 calculations for. And even though I only ask you 1 question, it's pretty common that I'm going to ask you to solve for something. But in order for you to solve for, say, delta x, we're going to have to solve for something in the y direction first. We're going to have to solve for t. T is the only thing that we can carry from one to the other. T is the only thing that is in both columns. So it's a pretty common process that we have to solve for t in the opposite column of what our final answer is. It's pretty common. It's not always the case, but it's almost always the case. Now, if you want, you could try to do equation number 3 right now in the x direction, but you're going to hopefully very quickly find out that you need a t, and you can say, well, I'm going to erase this in 1 second, but why can't I just use equation number 4? Don't write this, because equation number 4 says final velocity in the x direction squared times is equal to my initial velocity in the x direction squared plus 2 times ax times my delta x. I can solve for delta x, and I don't need time. That would be true, except for the fact that this is 0. My x term cancels out. And what you find out with this, your final velocity squared is equal to your initial velocity squared. If you take the square root of that, you can say my final velocity is plus or minus my initial velocity. That's also a true statement, but it's not getting us to where we want it to be. So we're gonna have to solve for time in the y direction first. So a given Fab 5 equation has four variables. You need 3 out of the 4 in order to solve. If we could solve for this here, then we could put it in here, and then we could solve using equation number 3. Given the information, I don't have final velocity in the y direction. It doesn't tell me how fast the tennis ball hits the ground. It doesn't tell me that. So I don't. So because of that, we choose the equation that doesn't have final velocity. Just for the record, we use equation number 3 a lot. It's not the only one we use, but it is very commonly used. In equation number 3, modifying it slightly to match our 2D motion problems now, is going to say delta y is equal to VIY times t. So notice how I added the y subscript next to my VI. Plus 1/2 AY, notice how I added the y subscript next to the a, times t squared. Looking at only my information in the y column. This is a y, delta y, this is only for my y column. This is a y column calculation. We only look at the information in the y. My initial velocity in the y direction is 0, so 0 times t is 0. That whole term cancels out. When we start plugging in numbers, my delta y is negative 0.8, which is equal to 1/2 of negative 9.8 times t squared. I'm changing colors just for contrast, no rhyme or reason, like I did before up in the table. But 1/2 of negative 9.8 is negative 4.9, so this is negative 0.8 is equal to negative 4.9 times t squared. In order to get t squared by itself, we need to divide both sides by negative 4.9. And we find that this is 0.163265306. And I'm just going to write 0.16. But that's equal to t squared. And when I take the square root, my calculator has lots more decimals in it. I'm not going to take the square root of 0.6. I'm going to take the square root of 0.16. I'm going to take the square root of the whole thing. And there's lots of different ways you can do that. But basically, I'm going to take the square root on this calculator, and I'm going to say of my answer, and it's just going to paste in every single decimal that I could ever dream of. And when we take the square root of both sides, we get a t is equal to 0.404018. Lots of decimals. And I'm just going to record 0.40. But when I do that next calculation, I'm going to use every digit that I possibly can. So now that I know that this is 0.40 seconds, that's how long it took to drop 0.8 meters. Now I can go through and say, well, that must be how long it's going to take to move left and right. So I know my time in that column. And now once we've determined time, we can then use that time for my last and the actual calculation we want. Tip for the projectile motion in the x direction, is to use equation number 3. Equation number 3 says delta x is equal to vix times t plus 1/2 ax times t squared. Okay, and that's my equation that I'm going to use. And because my acceleration in the x direction, we're talking the x direction, because my acceleration in the x direction is 0, ax is 0, 0 times 1/2 is 0, 0 times t squared is 0. That's why equation number 3 is a nice one. Delta x, which is what we're solving for, is equal to my initial velocity, 1.2 times 0.40. Delta x is equal to, now, again, my calculator still has my full decimal, all the decimals in there. So instead of just saying 1.2 times 0.4, I'm going to say times, and it's going to say my answer, times 1.2. And what I get is I get a value of 0.4848 something, 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 something. But I'm good to 2 decimals, so if I follow the rules of rounding, we're left with 0.48 meters. And that is how we do a projectile motion horizontal launch problem, if it's solving for how far it moves in the x direction, which is what this problem was. This is a horizontal launch projectile 2D motion. Any questions I can answer? Again, pretty typical that we go through and we solve for time in the opposite direction first, and then we move and we solve for the actual thing we want. You gotta solve for time first. Very general, typical thing. All right, let's take a look at problem number 2 then. Problem number 2 on the in-class activity talks about Cupid and Cupid's love arrow. So Cupid shoots an arrow horizontally. That's probably something we're going to want to remember. Shoots an arrow horizontally, not at some angle, horizontal, flat to the parallel of the ground. Okay, horizontally at a velocity of 100 meters per second at an unsuspecting high school student, 24 meters away. How far will the arrow drop before reaching the soon-to-be love-struck student? Okay, so that is the problem being asked. I think pictures are helpful. I am not the best artist, and I know that, but I still think they're helpful. So there's my arrow. Here's my student. And if there was no such thing as gravity, it'd shoot that student in the chin. But we gotta get him in the heart, right? Isn't that what happens with Cupid? We got him, well, let's move his arms then. We gotta get him in the heart in order for that student to follow along. So what we're trying to figure out is if, because there is gravity, the arrow's gonna do something like that. It's gonna drop. It's gonna be parabolic in nature. It's just really only the second part of it. And what we're trying to figure out is how far did it drop? So assuming we get him in the heart, how far did above the heart did we really, I think that's really kind of the question without directly being asked. And it gives us a little bit of information. It tells us from the arrow to the student, it's 24 meters. And it talks about an arrow is shot horizontally at 100 meters per second. I messed up my sorry, color coding. I'm trying to do color coding. My color coding is going to be red for the problem. 24 meters, 100 meters per second. How far did it drop? That's going to be red because that's for my problem type. Black. Is it a 1D or a 2D motion problem? 2D. 2D. So because it's a 2D motion problem, according to my problem type sheet, because it's a 2D motion problem, I have to make two lists of variables. I need to make a delta y, vi, oops, sorry, that's an x, delta x, vix, vfx, ax, and t. And I need to make a delta y, a viy, a vfy, an ay, and a t. The time is going to be the same in both columns. 2D motion problem. Black marker, done. If it's a 2D motion problem, is it a projectile or not a projectile? So Cupid shooting a love arrow at an unsuspecting high school student, how far will it drop? Is that a projectile motion problem or a non-projectile motion problem? Projectile motion problem, Mr. Davies. Very nice. So because of that problem type, my acceleration in the x direction is 0. And because my acceleration is 0, that means my velocities in the x direction are constant, which means these two are going to be the same. Whatever that number is, I know, but whatever that number happens to be. And because it's a projectile, the acceleration in the y direction is equal to negative g, and because we're on Earth, that value is down negative 9.8 meters per second squared. Green marker is because it is a projectile motion problem. Is it an angled launch or horizontal launch? Is the arrow shot at some angle, or is it shot flat or parallel or horizontal to the ground? And it says the arrow is shot horizontally, so therefore it's a horizontal launch. Blue marker is going to tell me that my initial velocity in the y direction is equal to 0. And then we're done with problem types. There's no more information we can pull from the problem type. Going back to the red marker from my problem, we have to now figure out 24 meters, well that's the displacement. Which displacement is it, x or y? Sure looks like your x direction, Mr. Davies. I would agree. Our question mark, sorry, I forgot to write it. Yes, that's your delta x, so we can put 24 there. My question mark is how far will it drop? That's my question mark. And lastly, it's shot at 100 meters per second, which is going to be my velocity in the x direction. Remember, I need 3 out of 4 variables. I need to know 3 out of the 4 numbers in order to solve for a fat 5 equation, except for equation number 1. But I only have 2. So what we're going to have to do is we're going to have to solve for time in the x first, and then use that time for the y column. Suggestion, because this is equal to 0, is to use equation number 3. So in the x direction, equation number 3 says delta x is equal to vix times t plus 1/2 ax times t squared. That's my equation. And notice how I write the equation before I put any numbers in every single time. And I've been doing these problems for a long time. And I still do it like that each and every time. Even when I'm making answer keys, I still write the original equation. Unless I'm really, 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 really in a hurry, and then I sometimes regret it because I make a silly mistake. I strongly, strongly, strongly encourage you to do that. So we can say, hey, look, my acceleration in the x direction is 0. So because this value right here is 0, that whole back term cancels out. And now we can plug in numbers. My delta x is 24. My initial velocity in the x direction was 100. and I can solve for t. Or I'm sorry, I take 24 is equal to 100 times t. Now to isolate t, I divide both sides by 100. And we get a time of 0.24 seconds. We get a time of 0.24 seconds that we can put now in both of those locations. But now that I have a time, now I have 1, 2, 3 numbers, and I can solve for that fourth. Once again, I don't know final velocity in the y direction. Sometimes we know that information. It's not a super common thing though, and because it's not a super common thing, we will use equation number 3 in both the x and the y a fair amount. Because if you go through and you say, well, a car drives off of a cliff, it's easy to say, hey, the car was going at 50 miles per hour. It's not a common thing to know, like, oh, but vertically, they were going 63.8 miles per hour as they hit the ocean or as they hit the canyon below. That's not a super commonly given information. It's possible, but you just realize that. So because this is often not given, we still often in the y direction use equation number 3 as well. Don't always use equation number 3. You should still be asking yourself, what equation should I use? Just if you find yourself using equation number 3 a lot, it's okay. It's not unheard of. So equation number 3 now for the y direction says delta y is equal to vi y times t plus 1/2 a y times t squared. Because my initial velocity in the y direction is 0, because this number is 0, that whole term cancels out. When you start plugging in numbers, delta y is equal to 1/2 times negative 9.8 times t squared, which we already calculated to be 0.24. That's squared. Calculator time 0.5 times negative 9.8 times 0.24 squared. We get a value of delta y is equal to negative 0.28224. Because we follow rules of rounding and I say 2 decimals is good enough, that we can just say, hey, it drops negative, going down. That's what that means. It means down. It goes down 0.28 meters. Now, sometimes people kind of get hung up on but should it be a positive? Well, it went down 0.2 meters or it dropped 0.228 meters, which why we have a negative. But some people would say, well, isn't going down a negative, is that like a double negative and therefore you shouldn't put the negative? I'm going to say it's okay to leave the negative, and I would encourage you to leave the negative because it's saying that the arrow is going down. Okay? So that's how I kind of think of that. So that's how you set up, this is again a 2D motion, projectile, horizontal launch problem. There is a worksheet that I'm going to, they're on the corner of that. Hey, you probably are going to want to come up and grab. Okay, it's your homework sheet for tomorrow. So people in virtual land get to stare at the screen for a second while you come up, and not tomorrow. Tomorrow's no school day on Monday. Okay, so come up and grab that if you want a paper copy. Otherwise, it is linked electronically as a PDF via Canvas. And I want to spend just a few minutes talking about a particular problem on this. So on the worksheet called Projectile Motion Problems. Projectile motion problems, welcome back everyone, you don't have to stare at the screen anymore. Projectile motion problems worksheet, you would assume that they're all projectile motion problems, which would be pretty logical and a pretty good way to title it, except for some reason it's not. So let me look at almost all the problems we do in this unit are projectile. There's a few that are not. Question number 3 on that homework sheet is not a projectile motion problem. And the reason number 3 is not is it is not moving freely through the air in 2 dimensions. So let's take a look at number 3. I'm just going to kind of give you a few tips for it. It says Joey is paddling at 1.5 meters per second across a 9 meter wide swift flowing river with a current of 2 meters per second. So we're talking about Joey paddling a boat, a canoe, a kayak, something across the river. Okay, so what's going to happen to Joey as he paddles across the river? So if we go through, and if we were to say, well, pictures are, here's the river. Okay, the river is 9 meters wide from here to here. Joey is in his boat and has his paddle, and he's going to paddle across the river. Now let's just pretend for a moment there was no current. What would happen is Joey would go like that, assuming he's a decent paddler and can actually paddle in a straight line, which is actually challenging to do. But the idea is, hey, we're going to go straight across. I shouldn't say showing, it takes some practice. But that's not the case because there is a current. The river is flowing down. So Joey's going to paddle across, I think it's at what, 1.5 meters per second? Yep. And the river's flowing at 2 meters per second. So because Joey's going to paddle straight across, what's going to happen is he's not going to end up here, he's going to end up here somewhere, right? Now, because he's paddling in the x direction and the river's flowing in the y direction, based upon my picture, I drew the river this way, he's paddling this way. The idea is it's a 2D motion problem. However, when we look at the, is it a projectile? Is Joey moving freely through the air in 2 dimensions? No, he did not go off of a waterfall. He's paddling across the river. He's not falling through the air. So when we go through and we make our list of variables, yes, it is a 2D motion problem. It is a 2D motion problem, and the time is going to be the same. There's a couple things I want to try to kind of help you with. So if I'm saying Joey is paddling in the x direction, I'm going to tell you Joey paddles at a constant rate. He's not going to get tired out. He is going to paddle at a constant velocity, so his velocity is going to be the same. Therefore, his initial velocity and his final velocity are going to have the same value, which means Joey's acceleration in the x direction is 0. And I'm also going to say that the current of the river here versus here versus here versus here is also the same. So I'm going to say this is the same. This is the current of the river, and it's also going to be moving at 0 meters per second squared. So we're going to say the river's flowing at a constant rate. We're going to say Joey's paddling at a constant rate. So yes, it is a 2D motion problem, but it is not a projectile motion problem. So then you really just got to go through and say, well, where does this 9 meters, does it go in X and does it go in Y? And we're trying to figure out how far does he end up down the river? Is that an X or a Y? What's my time? And there's a couple parts A, B, and C to kind of get you through that. With that said, you have some time. You have about 12 minutes left of class. I would strongly encourage before you walk out of here today on that homework sheet to set up the first problem, 2 problems, get started on these. These take some practice. They're a little bit different than a 1D motion problem, but by doing them here in class today, hopefully you can kind of get some of the issues of like, well, how do I know which one these are? You can ask me, we can have that conversation. And it'll help you be better prepared to do this homework sheet on Monday during your virtual learning day. So if you have any questions, please let me know.